Welcome to this first lecture of this course, which is named the first or a first course in number theory. And I don't have much to say, let's just get right into it. So first we will recall some of the notations and also discuss some prerequisites. They are minimal. So what is this notation? This is the set of all the natural numbers. And one way to write it is the following. And I believe this is probably the only way to write it. All right, then we have the set of whole numbers, which starts with 0. Some people also write a fancy W, but I prefer this thing. All right, then we have the set of integers, which may be written like this. Then all rational numbers. And one way to express this set is the following. P divided by Q, where P is any integer and Q is a natural number. Right? Then we have all real numbers. And there is no succinct way of expressing that. This is all complex numbers, which may be expressed as follows. This is a quantifier called the universal quantifier. That's just a fancy way of saying for all. That's exactly what it is. For all or for each, depending on the context, or for every, and so on. This is called the existential quantifier, which is a glorified way of saying there exists or there is, depending on the context. So already I'm kind of assuming that you're familiar with how to write sets. So this is part of the prerequisites. You should know the language of sets, intersection, union, how to write a set in builder form, roster form. Then we need to know about functions, injective functions, surjective functions, bijective functions, pre-image, image, maybe some other things, and also relations. So particularly we need to know about equivalence relations. All right, and the binomial theorem. So before I talk about binomial theorem, let me mention that all of these are covered on my channel in a separate playlist called Kickstart. So you can check out this playlist. All of this is covered. As of the making of this video, I think the current versions are well made, but I do plan to upgrade them in sometime in the future. Some more things will be discussed here, perhaps, and maybe a redoing of this is also needed, but as of now, I'm happy with the output, but I do want to improve it. All right, so what is the binomial theorem? Suppose you have any two numbers, they could be complex numbers, but if you're not very comfortable with complex numbers, we are not going to use complex numbers in this course too much, or maybe not at all. So if you're not comfortable with complex numbers, just think of A and B as real numbers, and I encourage you to learn about complex numbers on the side. If you haven't done that in high school, it is a very good time to learn about them. So what is the binomial theorem? It says that this can be expanded in the following way. This is nothing but n choose 0, which I will talk about what that notation is. A to the power 0, b to the power n plus n choose 1, a to the power 1, b to the power n minus 1, plus n choose 2, a to the power 2, b to the power n minus 2, and so on, up to n choose n, a to the n, b to the 0. And what is this n choose r thingy? N choose r is n factorial divided by r factorial times n minus r factorial. That's probably the worst way to define n choose r, but that's not wrong. N choose r is the number of ways you can select r things out of n different things. It turns out that it has this formula. And what is this n factorial? N factorial means n factorial is just the product of first n natural numbers. That's the definition. By convention, 0 factorial is 1. That's it. So that summarizes mainly the prerequisites, and I would humbly submit to you that this is not at all a lot of prerequisite. It's perhaps the bare bones that you need to know to read any piece of mathematics. All right. So the topic of today's lecture is division. It is a particularly simple concept. We are familiar with it. We have been dividing things in high school since, I think, very early days. So consider the following statements. If I say 2 divides 4, or 3 divides 27, or 5 does not divide 26, you will agree what that, you'll agree with all these statements, I'm sure. And that calls for a formal way of defining what is meant by division. So fix any two integers a and b, and we are saying integers, not natural numbers, any two integers where a is non-zero. So then we say a divides b if, let's write down the definition formally, even though we know what that means, but let's write it down properly. So we say a divides b if there is some integer q. So this is a notation. When we write q and then make the symbol and then some other set, this just means in or belongs to. Let me record that separately. So this is read as in or belongs to or member of or some other similar thing. Right? So what are we saying? A divides b if there is q in z, meaning the set of all integers, such that aq equals b. Right? And when we said 2 divides 4, you can see, just think of a as 2 and b as 4, and what you have is 2 into 2 is 4, so a is 2 and q is 2. 3 divides 27, 3 times 9 is 27. This is q, sorry, something happened. This is q, in fact it even looks like a q. This is q and this is a, this is b. Lastly, 5 does not divide 26. There is no integer which you multiply by 5 which can give you 26 as the output. 5 times 1 is 5, times 2 is 10, times 3 is 15, times 4 is 20, times 5 is 25, times 6 is 30. 26 doesn't come in the way. Alright, so that's the definition of division, but we will use this very convenient notation. So when we write, when a divides b, or maybe even better, a divides b, this statement will be written as, or can be written as, not necessarily, but can be written as, you write a, make a vertical bar, write b. Alright, so very convenient. Every time writing this in English is not very, it takes a lot of time and also takes a lot of space. Okay. And I just want to mention or emphasize that when we say a divides b, we implicitly mean that a is non-zero. We will never say 0 divides something. Right? So whenever we write this, it is already implied that a is non-zero regardless of us mentioning it. That in the definition of division, already we are defining only when a is non-zero. So this already implies that a is non-zero. Okay. So now let's discuss some properties of division very quickly. These are very, very simple properties. So note that a divides 0 no matter what a is, and of course, no matter when I say no matter what a is, no matter what non-zero element a is. A divides 0 already implicitly means that we are taking a to be non-zero. So why is it true that a divides 0? Well, a times 0 is 0. So therefore a divides 0. Why does 1 divide A? The second one says that 1 divides A. Why is that? Because 1 times A is A. Right? This is your Q in this case. In the previous, if you refer to the previous slide. Why does A divide A? Because A times 1 is A. I hope you're able to connect with the definition. At any rate, this is very, very familiar from high school. Okay. The second statement says that if A divides 1, then A is either plus 1 or minus 1, and conversely. If A is plus 1 or minus 1, then it divides 1, but that's moot because, both statements are kind of moot. But just notice, if you have A and suppose A is a positive integer which is greater than 1, then this division cannot happen. I don't want to write down a proof or anything of it. Let's just accept this as at face value. And if A is a negative integer, it cannot be less than minus 1 for it to divide 1. So this is a trivial statement, but all of the statements will be trivial, but I wanted to isolate it separately. Okay, another one. Suppose A divides B and C divides D. Then we want to say that AC, the product of A and C, divides BD. Perhaps it is better to put a bracket here, just so that there is no confusion. Right. So why is this true? Since A divides B, what we have is A times Q equals B. And since C divides D, we have C times R equals D for some integers Q and R. So if we multiply these two equations, we get ACQR equals BD. So this is AC, and then we have multiplied that with QR to get BD, and therefore AC divides BD. That's what we have written. So that's the proof of this. If A divides B and B divides C, then A divides C. This is kind of a transitivity that is happening. A divides B, B divides C, then A divides C. Again, very simple. A divides B meaning there is some Q for which this equation holds, and B divides C says that there is some R, some integer R for which this holds. But now we multiply the first equation by R on both sides. So we get this. But what is BR? BR is C. So this shows us that A times QR equals C, and therefore A divides C. Okay. Next is, if A divides B and B divides A, then B is plus minus A. So this fifth one generalizes the second one because A divides 1 and 1 already divides A. 1 divides everything. So this is a generalization of the second one, and let me not prove this formally. I leave this as an exercise. At any rate, we are able to easily believe it. If A divides B and B is non-zero, then the size of A is at most the size of B. Perhaps this should come before the fifth one or the second one. But what we are saying is that if something divides a number, then the magnitude of that cannot exceed the number. Again, I don't want to give a proper proof of it. There is no point. It is going to take us into things which I don't want to get into. I hope you're able to easily accept this. If A divides B, then the magnitude of A better be smaller than or at most the magnitude of B. Just like 7 cannot divide anything smaller than 7. Like 7 cannot divide 1 or 3. 7 can divide minus 14. But in the sense of magnitude, 7 cannot divide something smaller than it. Okay, so that's that. And if A divides B and A divides C, then A divides any integer linear combination of it. What is an integer linear combination of B and C? Anything of this sort where X and Y are integers. Okay, so let's prove the seventh one. Since A divides B, we know that there is some Q for which this equation holds. Since A also divides C, there is some S for which this holds. Multiplying the first equation by X, we obtain this equation that AQX is BX. Multiplying the second equation by y, we get ASY is CY. And now adding these two equations, we get AQX plus ASY equals BX plus CY, which gives AQX times SY, A times QX plus SY is equal to BX plus CY, and that's it. That shows that A divides BX plus CY. So that's very nice, but of course, we all know these things. All right. So here is a nice example. This is not obvious. Why should 7 divide this for every natural number n? So if you put n equals 0, I have stated it only for n greater than or equal to 1. I could easily write 0 here, but anyway. So if n is equal to 1, what is this? This is 8. 8 minus 1 is 7, and 7 divides 7. What if n is equal to 2? 3 times 2 is 6. 2 to the power 6 is 64. 64 minus 1 is 63. And 7 divides 63. So you can experiment. You can put further values of n, but very soon you would not be able to compute it. If you put n as 7, that is too big a number to compute and verify this. So even for small values of n, we would like to see a proof of it. We want to see a proof which works for all values of n. So anyway, at some point the computation was bound to fail. But even for small values, it is unclear. So let's try to prove this. And I encourage you to pause the video and try to think of a proof for yourself. Later in the course, we will develop techniques which will make these questions almost trivial. As of now, this may seem like a difficult question. But with some more techniques, this will become absolutely trivial. You can do these things mentally. But for now, we can't do it mentally. So what we have is, first of all, this thing is 8 to the power n plus 1. Right? 2 to the power 3n is same as 8 to the power n, which we will write as 7 plus 1 to the power n. Sorry, it's not a plus 1. We are interested in minus 1. What I had written was not wrong, but was not what we were trying to evaluate. So 7 plus 1 to the power n, we will use the binomial theorem. N choose 0, 7 to the power 0, and times 1 to the power something, but I won't write the 1 to the power something because 1 to the power anything is 1. N choose 1, 7 to the power 1. N choose 2, 7 to the power 2 plus n choose up to n choose n, 7 to the power n. And that thing is lessened by 1. Now, what is this guy? This guy is 1. This is 1, that is 1. So that cancels out with that. So what we are left with is the following. N choose 1, 7 to the power 1. N choose 2, 7 to the power 2. And this will be added up till n choose n. And now observe, this is divisible by 7, right? It has already a number that is divisible by 7. So perhaps you can write another property. You can say that if A divides B, then A divides BC for all integers C. And this is another property that we did not see explicitly, but of course this is true. So this is divisible by 7. Similarly, this is divisible by 7 because this is, and so on and so on. Every term here is divisible by 7. So this is divisible by 7, this is divisible by 7, this is, and so on. And if two numbers are divisible by 7, then so is their sum. Any integer linear combination is. This is divisible by 7 and this is, so their sum is also there, but this fact has nothing to do with just two of the numbers. You can extend that to any n numbers. So again, what we are saying is that if A divides B1 up to Bn, then A divides their sum. If A divides each of B1 up to Bn, then it also divides their sum, a trivial property. We saw this in the form of integer linear combinations in the previous slide, but it was only for 2, when n is equal to 2, but you can easily extend it for any finite n. So that's it. Each of these are divisible by 7, so the whole sum is also divisible by 7, and that's it. 7 divides this guy. A lot of time spent on a very simple problem. Let's move on. Let me end this lecture by defining what primes are and maybe mention 2 interesting questions about primes. So natural number p is said to be a prime if the only divisors of p, if the only natural numbers that divide p are 1 and p. However, we do not count 1 as a prime. So, let me just, this is not the way I wanted to write it, but I want to say that and p is greater than 1. So we do not regard 1 as a prime. There is nothing technically wrong with it. It's just that it will cause so many exceptions that it is better to not regard 1 as a prime. So natural number p is said to be a prime if, first of all, it has to be greater than 1. And once it is greater than 1, the only natural numbers that divide p should be 1 and p, nothing in between. We'll see examples, but I'm sure you have seen this concept in high school. This statement that the only natural numbers that divide p can be shortened by saying the only divisors of p. So here let me make a remark. If a divides b, this is a definition. If a divides b, then we say a is a divisor or factor, maybe some other synonyms also exist, divisor or factor of b. Okay, so just some definition. And now let's see examples of prime numbers. As we saw, 1 is not a prime. What about 2? What are the natural divisors of 2? 1 is a divisor, 2 is a divisor, and of course, those are the only 2 divisors in natural numbers. So 2 is a prime. What about 3? 1 is a divisor, of course. 2 is not. 3 is. So the only divisors of 3 are 1 and 3, and therefore 3 is a prime. What about 4? 4 is divisible by 1, of course, 2, and 4 itself. So it has an extra divisor, and therefore this is not a prime. 4 is not a prime. 5 is a prime, just check. 6 is not a prime because it is divisible by 2 and even 3, and of course by 1 and 6, so this is not a prime. And let me now list out some of them. So 7 is, and then 11, 13, 17, 19, 23, and so on. Okay. And let me write down or discuss 2 of very interesting questions about primes. Primes have a fundamental role in number theory and in all mathematics. Hersh, the great mathematician Paul Hersh, is reported to have said that it will be another 1,000,000 years when we will understand the primes. So even now they are at the forefront of number theoretic research. And 2 of the questions that have preoccupied mathematicians for a very long time, and both of them have been satisfactorily answered, but better understanding is always possible. So one question is, how frequent are the primes? Meaning, suppose you take a big natural number n and ask how many primes will one encounter within the first n natural numbers. Can we write it down or express that number in some way? And the answer is yes. It's roughly about n upon log n. So many primes exist in the first n natural numbers. This is, of course, n upon log n is not even a natural number. So you might say, how can one say that there are so many primes? But in a very precise sense, those are the fraction of primes that you see in the first n natural numbers. And second is, suppose I give a number, write down a big number. Can we develop a test which will tell us whether or not a given number is prime? Right now, what do? We just list out all the numbers that are smaller than that number and check one by one which are the divisors. For example, for 23, I'll go 1 of course divides 23, 2 does not, 3 does not, 4 does not, and so on up until 23. And I will find that only 1 and 23 are the divisors, therefore 23 is a prime. So this is a very expensive procedure. It takes a lot of time. So is there a better way to test for primes? And this is an achievement of Indian mathematics. There is an algorithm by Agrawal, Kyle, and Saxena. It's called the AKS algorithm. It's a big achievement in computer science, which gives an efficient way to test if a given number is prime or not. Right? So we will not be discussing this algorithm in this course, but just for your general knowledge, I'm mentioning this. And maybe we will see something towards this in this lecture series. Maybe. If not, then we will discuss it in the second course on number theory, which I talked about in the course announcement. First, we will finish this course, which is the first course in number theory. Then you can learn linear algebra. Then you can learn group theory. And then there will be a second course in number theory. And maybe I'll discuss it here, if not in this course. All right, so talked about too much for too long, given that the lecture was particularly simple. So I want to end it here. As usual, like, comment, share, subscribe, and I will see you next time.